Hey guys, now in this video we will try to solve a segment tree problem, and I have taken this problem from Codeforces around 380, and this is a C problem in that context. And this the name of this problem is Sereja in brackets. So this is the input which will be given to you. So the input is a expression, a left parent and right parent expression, and followed by the number of queries which we will make. So here it is 7, so that means there will be 7 queries. So the query will be of type L to R. So here 1 1 means from index 1 to index 1, and 2 3 means from index 2 to index 3. Okay, and what the problem is basically asking us is to find the length of maximum correct bracket sequence from the queried L to queried R. That means, for example, if this is the given bracket sequence, then the query is from 8 to 12. Then what I'm going to do is I'm going to find the length of maximum correct bracket sequence from index 8 to 12. So here we can see that these 4 parents makes a correct brackets subsequence, and here the right parent at index 12 doesn't have a corresponding match, so we are just dropping it off and we are saying that the answer is 4. And similarly, if you see what is the answer from 3 to 7, then the answer from 3 to 7 is, you can see these 4 characters or parents make a correct bracket subsequence, and that is maximum. We can't go more than that. And 5 to 6 is also an answer, but this is not maximum. We have to find the maximum correct bracket subsequence. So I think you are pretty much clear about the problem, what it is asking for. So you will be given like Q such queries, and you have to answer all such queries. Okay, so what is the obvious solution here? The obvious solution is you will do a brute force approach. So you will try to loop from 8 to 12, and you will try to find out, and basically like you can just find it out the brute force way. I'm not going to discuss it here. So just pause this video and try to find out a segment tree solution for this problem. Okay, so now let's move to the solution. So as I said, every segment tree node has a structure, and that you have to define for a problem, and for a particular problem the segment tree node structure is different. For different problem the node structure is different. For this problem the node structure will be like this. We will have 3 variables. One is the answer, that is the length of maximum correct matches from range L to R, and LP denotes the number of left parentheses that is remaining to match, and RP denotes the number of right parentheses that is remaining to match. And this node holds the responsibility from node L to R. Okay, and now let's see how are we going to build this segment tree. Okay, so I have already drawn the tree, and I know that I've explained this how to build this segment tree in the previous video, so you can just get back to the previous video and try to understand how do we build this tree. So now you can see that every node has 3 variables. Like I have drawn it in some way so that it is like visually clear. That's why I have taken a node and I have drawn like 3 spaces in that node. Okay, so now let's see how are you going to build this. So now I will start with the root node, and we will go to the left subtree, and then again we will go to the left subtree, and then again we will go to the left subtree, and then again we will go to the left subtree. And when we have reached a leaf node, Okay, so that is index 0 0. Okay, so like you can just clear it out and write that this is our index 0 1 2 3 4 5 6, like in that way. So in index 0, what I have is I have a left parenthesis. So here I'm updating my count of left parenthesis by 1, and obviously it is not a right parenthesis, so this is 0, and my answer will be 0, because if you have a single like parent, we are not going to do a match, right? You need at least 2 characters to make a match, so obviously the answer is 0 in a leaf node. So this is how we fill a leaf node. Okay, and then from here, when we have filled the leaf node, we will get back, and then we'll go to the right subtree and build it. And as I said here, like in index 1 1, we see that it's a right parent, so I'm going to update it to the 1, and obviously this is not a left parent, so this is 0, and the answer is obviously 0. And from here I will get back again to this node. Now we will see how to merge the two subtrees, the left subtree and the right subtree. And here we need to see how we are going to merge it, so that we maintain the consistency of the segment tree. Okay, so let's move and see how are we going to merge. So this is how we do a merge. So let's say I'm standing on this node, okay, and I have completed finding the answer for left subtree and for the right subtree. Okay, and here I can see that the answer is 2 for the left subtree and the answer is 3 for the right subtree, and the number of parents, the number of left parents which is remaining to match is 3, and this 3 is nothing but these 3 are remaining to be matched. Okay, and here there are 2 right parents which we need to match, which is remaining, so this is the 2 left parents which is remaining, and similarly you can find it out in this subtree. So now we are going to merge this left subtree and right subtree and update accordingly in the node I am standing on. Okay, so first what I will do is I will find the minimum of the number of remaining left parents in the left subtree and the number of remaining right parents in the right subtree, this 2 and 4. I will find the minimum of that, and then I will put it in a variable called match. That means if we merge these 2 subtrees, okay, or these 2 expressions, then if there are like 3 left parents and there are 4 right parents, right? Sorry, if there are 4 right parents, then how many matches are there? These 3 and these 3 can match, right? So this is a match. So we have 3 matches here, and this is dropped off. That is why we are taking the minimum of 3 and 4. So that is 3. Okay. Now we are going to update the answer. So previously in the left subtree we had answer as 2, and in the right subtree we had 3. So we will do 2 plus 3 plus the number of matches, because when we are merging we are getting more matches. Okay, so now in this match we have 3, right, as I said. So here the answer will be 2 plus 3, we will have 2 plus 3 5, 5 plus 3 will be 8, so this will actually be 8. Okay, so these are the number of matches we are having at this node. Now we have to update the number of left parents remaining and the number of right parents remaining, because when we are adding up this match we have already eaten up the minimum of L.lp and R.rp. So we have to subtract that from the sum of the left parents from both the branches. So now we are going to update the number of remaining left pointers. Okay, and that will be the sum of the left pointers and the right pointers, so I mean right parenthesis, and the number of matches which we have already have eaten up. Okay, and similarly for the right parenthesis. Now this is the way we are going to merge the two subtrees so that we maintain the consistency of the tree. So now I am going to fill it up. Okay, so here you can see that the minimum of this guy and this guy is 0. Okay, sorry, minimum of this and this, because we will do the minimum of the number of remaining left parent on the left subtree and the right parent on the right subtree. So minimum of that is 1. That means we have 1. So our answer will be 0 plus 0 plus 1, because as I said, we will just sum it up and then I will add the matches we have in the left subtree and right subtree while we are merging. So the answer is 1 here. Okay, now we are going to update the number of left parenthesis remaining and the right parenthesis remaining. So here you can see that 1, so here we have 1 plus 0 minus the number of matches. So match is 1, so that's why it will be 0. Why it is not working? Sorry. So this will be 0, and then I will add up 0 and 1, and that is 1, and minus 1, so that is 0. So see here, this particular node says that from 0 to 1 there is one match and there is no left parent or right parent remaining to match. You can see that here in 0 to 1 we have exactly one match and there are no remaining left parent or right parent to match. Okay, so from here, when we have merged this, we will get back to this subtree, and now here I will go to the left subtree and build it. You can see that the 2 contains a right parent, so right parent will be 1 and this will be 0, and obviously this is 0 and this is 0, and 3 and obviously we'll get back here and then we'll get back here and we will update it, and obviously we will update it now. So now 3 third index contains a left parent, so this will be 1 and 0. Now we will get back from this guy. Okay, now we will get back from this guy and you will see that we will do a minimum of what? This guy and this guy, and this is 0. So the answer of this guy is 0 plus 0, that is 0 plus 0 minus 0, and that is 0. Okay, and now we have to fill the left parent. How many left parent are remaining? So this is 0 plus 1, that is 1. 1 minus 0 is 0, so we'll fill it with 0, and then we will do sorry 1 minus 0 is obviously 1. Why it will be? So this will be 1, and then we are doing 1 plus 0, that is 1. 1 minus 0 is 1. So now this node is filled. Now we will get back from this guy, and now we will merge the subtree on the left hand side and on the right hand side again. So here let's fill it. So now you will see that the minimum of 0 and 1, what is that? That is 0. Okay, so I have 0. Now what is the answer on the left hand subtree? That is 1. On the right hand subtree, that is 1. So this is my match actually. So 1 plus 0 is 1. Okay, and now we have to see how many left parent are remaining. So we will do so we will do 0 plus 1, that is 1, and match is 0. So here what we are doing is 0 plus 1 minus 0, and that is 1. Okay, and now we will calculate for the right parent remaining. So this is nothing but this is 0 and this is 1, that is 0 plus 1 is 1. 1 minus the number of matches is 0, so it will be 0 plus 1 minus 0, it will also be 1. So what this node is trying to say is, from 0 to 3, I mean this one, 0 to 3, we have one match, that is this one, we have one match, and we have one left parent remaining to match and one right parent remaining to match. So this is the left parent remaining to match and this is the right parent remaining to match. So this is how we build this segment tree, and I will leave the rest of the nodes for you guys to fill in. So you guys can try and fill this field and build this segment tree. So try on your own, and if you have any queries, then you can post it in the comment section. I will try to resolve those queries. So now we have successfully built the segment tree, and you understand what is the structure of this node and how are we going to build it. Now we will try to query it, because in this problem what do you have? We don't have any update operation. What we have is, you have a static expression, then just go and build that segment tree, and then you have queries, and queries are only reading queries. They will only read, okay, they are not going to update. So we will just build the segment tree and then we are going to make query. Okay, so now I have filled this segment tree, you can see. Okay, and now when I am getting back from a node, I will be returning a node, I mean a structure, and that structure contains the answer and the left parent remaining to match and the right parent remaining to match. That's it. Okay, so let's go through one of the query. So let's say the query is 2 to 5. So find the number of maximum correct bracket subsequence in the range from 2 to 5. Okay, so as usual, what we will do is we will start from the root node, and then we see that 0 to 12 and 2 to 5 is a partial match. So we will go to left subtree and right subtree, but first let's go to the left subtree. Now we see that 0 to 6 and 2 to 5 is a partial match, so I will go to the left subtree, and I will also go to the right subtree, but let's go to the left subtree first. Okay, now I see that 0 to 3 is also a partial match, so I will go to the left subtree, and here we have 0 and 1. So 0 and 1 and 2 and 5 are no overlap case, so I will return answer as 0. Okay, so let me return answer as 0. Number of left parent remaining to match is 0. Number of right parent remaining to match is 0. So in no overlap case, I will get back with 0, 0, 0. Okay, so sorry, I will try to do it in this way. And I'm going here, I'm just going with 0, 0, 0 value. Okay, so 0, 0 and 0. Okay, so as I said, now at this node we have a partial overlap. We'll go to the right subtree also. So we go to the right subtree and we see that 2 to 3 and 2 to 5 is a complete overlap case. So now when we are getting back from this node, we will get back with whatever is there in that node. So the answer is 0. We have one left parent to match and we have one right parent to match. Now we will again merge this node. Okay, and I have shown you how to merge the node. So just let's find out what will be the answer here. 0 to 3, right? It holds the responsibility from 0, 0, 0, 0. Okay, so now 2 to 3. So 2 to 3. Now in this case, obviously what you're going to do is you are going to update. Okay, wait. So now this is the left parent remaining to match, this is right parent, this is LP again, this is RP again. So what we do is we find the number of match first. So how many number of matches there? So obviously the match is 0, right? So if you find the minimum of left pointer 0 and here the right pointer is obviously 0. Now what is the answer? The answer is the answer of this, the answer of left subtree and the answer of right subtree minus the match. So 0 plus 0 minus 0 is 0. So while we are returning back from this node, we will return answer as 0. Okay, and then answer as 0, and how many left parent to match? So here you will have 0 plus 1 is 1, 1 minus 0 is 1. So I will return with 1 left parent, and similarly I will be returning with 1 right parent. Okay, so now here I will go to the right subtree from this node. Okay, and when I'm going to the right subtree, I see that 4 and 6 and 2 and 5 is a partial overlap. So I'll go to the left subtree here. Okay, and then I see that 4 to 5 is a complete overlap. So I will be returning back with 1 comma 0 comma 0 from here. Okay, and now I will go to the right subtree and I see that 6 and 6 is a no overlap case. Then I will get back from here. Okay, with what? If it is a no overlap case, with 0 0 0 I will return. Okay, now I have to merge these two guys now, and I can see that the number of match is the minimum of left parent here and right. So obviously it is 0. Again we have a match of 0, so number of matches equals to 0. And what is the answer? The answer will be the answer of the left subtree and the right subtree minus the match. So we have 1 plus 0 minus 0, that is 1. So now when we are returning back from here, okay, then we will be returning back with answer of 1. And how many left parent are remaining to match? So 0 plus 0 minus 0 is 0, and then the number of right parents remaining is 0 plus 0 minus 0 is 0. We are coming back with 1 0 0. Okay, now here we have to merge it again. So we have what? We have there's a clutter here. So we have this value from the left subtree and this value from the right subtree, and we have to merge it here. Okay, so then I can see that the number of match is minimum of the left parent and the right parent, that is 0. So again we have a match of 0. So we have 0, and now you have to find the answer of the left subtree and the right subtree. So that is 0 plus 1. So that is 1. So the answer at this node is 1. Let's write it here, man. Answer is 1. And now the number of left parent remaining is 1 plus 0, right? So 1 plus 0 is 1, and 1 minus the match was 0, right? I mean the match was 0, so obviously it will be 1, and the right parent will be equivalently 1 only. So here what I am saying is, when I am getting back from this node, that is this node, then I am saying that we have one match, and you can see that here we have exactly one match. Okay, 4 to 5, and we have one left parent remaining, this guy, and we have one right parent remaining, that is at 3. Okay, so that is what we are going to return it from here. Sorry, that is what let me erase it. Okay, so now from here we are getting back with 1 1 and 1. Okay, now here you see that 7 and 12 and 2 to 5 is a no overlap case. So I will just return with 0 0 and 0. Okay, now we have to merge it now. So here the temp is the minimum of the left parent and the right parent, that is 0. So that number of match is 0, and we will now add up the answer of the left subtree and the right subtree. So that is this one and this one, that is 1 plus 0. So we have 1 plus 0 plus 0, that is 1. So here I have 1. Okay, and now we have to update the left parent and the right parent. Okay, so here what we have is I can say, so here what I can say is it is the sum of this and this. So that is 1 plus 0 is 1, 1 minus 0 is 1. So 1, and similarly for the right parent also it is 1. So when we are returning back from here, we are having 1, 1 and 1. So the answer here is not 1 because this is the number of matches. So if the number of match is 1, then the answer will be the number of match into 2. So here the answer will be 2. You can see that from 2 to 5, okay, what is the answer? The answer is 2 because here is the answer and we have a length of 2, and there is no more matches we can make from index 2 to 5. Okay, and just remember that when I am making this recursive calls in a query, I'm not going to update my segment tree because we don't have a segment tree update. We are merging these two nodes and I'm just building a node and returning it back, and in that node we have the answer, the number of remaining LP and the number of remaining right parent. So that's it. Okay, so this is how we are going to query the segment tree for the answer. So what is the time complexity of this query? Okay, so the querying time is O of log n here. Okay, and what is the time to build this segment tree? Obviously O of 4n, because the maximum number of nodes in a segment tree we can have is 4n. Okay, so I will just I think we are towards the end of the video, and I've explained you the build and querying of the segment tree. So I will just share the code which I have submitted in Codeforces, and then you can go through the code and try to understand the flow of the code. Okay, and there is one thing I need to share, that is this is not obvious why the querying is O of log n. Okay, so I will make a separate video for that, like why this is log n, because you can see that when I'm coming to a certain node, I'm exploring the left subtree and the right subtree. So in this way you can say that we might end up exploring all the nodes in the segment tree, right? But that is not correct. So I will explain why the time complexity is O of log n in another video. So that I will do. Okay, so thank you guys. So if you like this video, so please subscribe, hit that like button and share with your fellow coders. Okay guys, thank you, bye.